This video continues the discussion on the rules of differentiation and their application on comparative static analysis and economics from the previous video, from the part 1. When we have y as a function of x1, x2, x3 and so on until the xn, the derivative of y with respect to x2, for example, is only a partial. It is only a partial derivative because y can also be found its derivative with respect to x1 or x3 or xn. So it is a partial derivative. To show that it is a partial derivative, the symbol of d is made differently here. And also, this partial derivative can also be written this way. f2, it shows that it is the partial derivative of the function with respect to the second x here, x2. Now let's see the derivative, the partial derivatives of this example. Y equals 3u minus 2v divided by u squared plus 3v. The derivative of y with respect to u is a partial derivative, as well as this one, the derivative of y with respect to v. It is also a partial derivative because we have a quotient here, so we can apply the quotient rule. Here we can see here that the quotient rule is applied. The 3 here is the derivative of the numerator here. The numerator is 3u minus 2v. The derivative with respect to u is 3. We have 2v here, and in this element of this function, we cannot see any u's here. So we can consider this as a constant, and the derivative of a constant is 0. So the derivative is only coming from the 3u. The derivative of 3u with respect to u is 3. And then multiplied by the denominator minus the numerator multiplied by the derivative of the denominator here. The derivative of this denominator with respect to u is 2u. Because we are paying our attention on the u and there is no u's here, so we can consider this as a constant, and the derivative of a constant is 0. So the derivative is only coming from the u squared here, and the derivative of u squared with respect to u is 2u, and then divided by the denominator squared, and then we can simplify this equation becoming this result. The same thing for the derivative of y with respect to v. We can also apply the quotient rule. This is the derivative of the numerator with respect to v. The derivative of this 3u with respect to v is 0 because it is now a constant, because we are talking about v now. And then the derivative of this minus 2v with respect to v is minus 2, and then multiplied by the denominator minus the numerator 3u minus 2v, and then multiplied by the derivative of the denominator. The derivative of this denominator with respect to v is 3 because now it is becoming a constant, and the derivative of a constant, because we are not talking about u but we are talking about v, the derivative of a constant is 0. So the derivative is only coming from this part of this function, and it is 3. The derivative of 3v with respect to v is 3. It is 3 here, and then divided by the denominator squared, and then simplify, and then we find the result of this partial derivative is here. Now we have another example of applying partial derivative. This time it is for market model. We have demand, we have supply, and A, B, C and D are all greater than 0. This is A, B, C and D are all greater than 0. And the equilibrium has also been given here. This is the price in equilibrium. The equilibrium price is AC divided by B plus D. And the equilibrium quantity is AD minus BC divided by B plus D. And before discussing the derivative, please pay attention that the derivative of q, the partial derivative of q with respect to a, here the derivative of q with respect to a is not the same as the derivative of q star or the derivative of the equilibrium quantity with respect to a. This one shows the derivative of q with respect to a. So what we are talking about is the demand function. And this one is talking about the equilibrium quantity. Okay, so the result will be different. The equilibrium price from the previous slide is written again here, P star, and it is also rewritten as A divided by P plus D, and then C divided by P plus D, and the A can be moved here, the C can be moved here, so we have this version of this P star, and then the partial derivative of P star with respect to A is 1 over B plus D. It can be directly found from the derivative of this version of the P star, because we have C times 1 over B plus D. There is no A here, so we can consider this as a constant, and the derivative of a constant is 0, so we can ignore this. And then we have A times 1 over B plus D, and the derivative is 1 over B plus D here. And then the derivative of P star with respect to B can be found here using the quotient rule, because we have a quotient here. The derivative of the numerator here with respect to B, there is no B here, so it is 0, times the denominator B plus D minus the numerator A plus C multiplied by the derivative of the denominator. Here we have P, the derivative of P here is 1, and because it is the derivative of P star with respect to P, and there is no P in this part of this function, so the derivative of a constant is 0, so it is only 1 here, divided by the square of the denominator, B plus D squared, and then we can simplify this, becoming this result. And then next, the derivative of P star with respect to C, it is also 1 over B plus D, the same result as P star with respect to A. So we can conclude that the derivative of P star with respect to A is the same as the derivative of P star with respect to C. And also, because we know that P is greater than 0, D is also greater than 0, so the derivative of P star with respect to A is greater than 0, as well as the derivative of P star with respect to C. And then the derivative of P star with respect to D can be found using the quotient rule, and the result is here, and it is the same as the derivative of P star with respect to D. And because we know that A is greater than 0 as well as C, P and D, so we can conclude that the derivative of P star with respect to B is less than 0, because we have a negative sign here, Now let's see the graphical illustration of the partial derivatives. This is the partial derivative from the previous slide, the derivative of P star with respect to A. This is the derivative of P star with respect to B. This is the demand, this is the supply function. So this is the supply curve, this is the demand, and this is the initial equilibrium. And then let's see the partial derivative with respect to A. In this partial derivative, we need to find the change in P star if A changes. A in this demand function is the intercept here. It is the quantity intercept. Because in this illustration, the quantity is put on the vertical, so the A is here. It is the vertical intercept of this demand function. So when A increases, the demand curve will move upward from T1 to T2. Here, A1 to A2. So the equilibrium point moves from E1 to E2. And the equilibrium price moves from P1 to P2. So we can see that if the intercept A1 increases to A2, the equilibrium price will move in the same direction. It will increase too, from P1 to P2. It is in line with the result of the derivative here, because the derivative of P star with respect to A is greater than 0. It means that when A increases, the equilibrium price will also increase. Let's see now the derivative of P star with respect to B. This is the initial equilibrium at E1. And then, for example, if B increases, P in this function, in this demand function, is the slope. So the slope increases. When the slope increases, while the A is held constant here, there is no change in A, so the A stays here. B increases means the curve becomes steeper, so it moves from D1 to D2. It rotates actually. It rotates from D1 to D2. And then the equilibrium point moves from E1 to E2 here. And then the price moves from P1 to P2. The price decreases. So we can see here, when the slope increases, it is becoming steeper. The P increases. The equilibrium price decreases. So it is in line with the result of the derivative here. The derivative of P star with respect to B is less than 0. It is negative. It means that when B increases, P decreases. Now let's see the graphical illustration of the partial derivative of P star with respect to C. C in the supply function is the vertical intercept here. Because Q is put on the vertical, so C is the vertical intercept. If the Q is on the horizontal, if the quantity is put on the horizontal axis, the C here will become the horizontal intercept. But because this time the illustration is putting Q on the vertical, so the C here is as the vertical intercept. So the minus C is here. This is the initial supply curve. So the initial equilibrium is at E1. When C increases, so the vertical intercept will move from minus C1 to minus C2 because C increases. So the supply curve will move from S1 to S2 here. And then the equilibrium point will move from E1 to E2. So the equilibrium price moves from P1 to P2. It means that when the C increases, here the C increases, the price in equilibrium or the equilibrium price will also increase. It is in line with the derivative here because the derivative is greater than 0. That means that when the C increases, the price in equilibrium will also increase. Now let's move to the derivative of P star with respect to D here. D in the supply function is the slope. So when the slope increases, for example, the supply curve will become steeper. It will rotate from S1 to S2. The minus C stays here, it does not change because we are not talking about a change in C, we are talking about a change in D. When the supply curve rotates from S1 to S2, the equilibrium point moves from E1 to E2, and then the price moves from P1 to P2. So when t increases, the equilibrium price decreases. It is in line with the partial derivative here. It is less than 0 or negative. It means that when the t increases, the equilibrium price will decrease. And for exercise, you can find the derivatives, the partial derivatives of the equilibrium quantity, the Q star. And you can also reverse the axis. Instead of using quantity on the vertical, you can also use the horizontal for the quantity, and then the price will be put on the vertical axis.